Well, friends, once again, I welcome you for my lecture number 7. Friends, in previous lecture, I discussed about the Hermitian adjoint of an operator, and we have discussed some important properties of the Hermitian adjoint. And we have also discussed the Smith orthogonalization method to find a set of orthogonal eigenfunctions of an Hermitian operator. You see, last time I have discussed several problems, and this problem, which you can see that problem number C was given for the homework. Let us revise this problem. You see, what we would like to derive is the operator product AB dagger is equal to B dagger A dagger. B dagger is a self-adjoint Hermitian adjoint of operator B. A dagger is a Hermitian adjoint of operator A. And you see this adjoint of operator is a self-adjoint, which we have discussed also. So now I want to prove this. So what I do, I take this product, scalar product, I take a psi1, and I want to prove AB dagger. So I take the operator product AB with psi2. So the first factor of the scalar product is psi1, and the second factor is AB operating on psi2. And now you see that A is a Hermitian operator, B is a Hermitian operator. So the product of the is also a Hermitian operator provided A commutes with B. So you have to consider this condition that you have an operator A and operator B are the Hermitian operators, and they are commuting with each other. So here we write this. So using this property, you see this is the property of the Hermitian self-adjoint. If A is a Hermitian operator, right? Okay, and so we can write the scalar product of psi1 A psi2 is equal to A dagger psi1 psi2, where A dagger is a Hermitian adjoint of an operator A. This is known to you. So I use this property here. You see this, the product AB. So I write down, you see here, instead of AB, you write the product AB, right? So it comes out to be AB whole dagger, you see. This is, so this write down AB whole dagger side by side. So this is the law which we have applied here. Look at this. So you have got an AB dagger side 1 side 2. And once again you go for the same way. You see now the AB dagger psi 1 psi 2, one can write, if it is the Hermitian, one can write psi 1 AB psi 2, right? Because we know that AB dagger is this is also a Hermitian operator. So AB is a Hermitian operator. So one can write AB dagger psi 1 psi 2 is equal to psi 1 AB psi 2. So I can use this law here, this law. So I can write psi 1 A B psi 2. Now you see I split AB, I take A operating on B side 2. I'm taking the B side 2 as a one unit. And now once again your A is a Hermitian operator. If A is a Hermitian operator, I can write A dagger psi 1 B psi 2 using this law. Psi 1 A psi 2 is A dagger psi 1 psi 2 if A is Hermitian. Okay, and self-adjoint. So you write down A dagger psi 1 B psi 2, this law, which I have used this law, right? And again, you know, now this is you can see this B is again a Hermitian operator. So again, using this law, psi 1, you see now instead of A psi 2, we have a B psi 2. See, so it comes out to be B A dagger psi 1. So now it is B dagger A dagger psi 1 psi 2. So ultimately, it gives you B dagger A dagger psi 1 psi 2. Look at the term here, right? So one can prove now that AB. So this is, you see that AB dagger psi1, psi2. Look at this. The AB dagger psi1, psi2 turns out to be B dagger, A dagger, psi1, psi2. Look at this equation. Look at this first term of the scalar product. It is AB dagger here. And here look at the scalar product here. Both the scalar product are same, right? And look at the first term here, B dagger, A dagger. So one can compare these two scalar product because they are equal. So one can write AB dagger is equal to B dagger, A dagger. That means the Hermitian adjoint of the operator product AB is simply a product of Hermitian adjoint of B with Hermitian adjoint of A. And this is a very important result which you people have to remember. And we will also take some example in an assignment to find the Hermitian adjoint of an operator. So we will take some examples in assignment, and I will also solve some problems to find Hermitian adjoint of an operator. So well, with this explanation, we may proceed for another example. Today I'm going to discuss some problems only. So you see, I have another example which I consider. Let us consider that you have one eigenfunction psi of x is given by a constant a, right? Exponential of minus x square over a square. This is our eigenfunction, and what we want to find, you have to find out the product of scalar product of psi with pxi. So you have to find this scalar product. The first factor of the scalar product is psi, that is the wave function. And the second factor of the scalar product is px operating on psi. So this is your psi, and now your operator p, momentum operator p, operates on psi, that is px psi. So you can see here, so first we will compute the second factor px psi. So you see, I write here separately, px is operating on psi. Px is a component momentum, x component of the momentum, and we write down its operator correspondence is minus ih cross d by dx. This is known to you. So we write minus ih cross d by dx operating on psi. And you can see minus ih cross I'm keeping as it is, and d by dx. Psi is our eigenfunction. Eigenfunction is constant a, exponential of minus x square by a square. So here I wrote this letter a is here. So please remember, this is the constant a here, right? Then exponential of minus x square by a square. The factor a is here. Please remember this. So you have to differentiate d by dx of exponential of minus x square over a square, and a is constant, so you take it outside. So I took a here, so it is minus ih cross a, and d by dx of exponential of x. So first your exponential factor remain as it is, and it becomes d by dx of minus x square over a square, the argument of the exponential function. So the argument of exponential function is minus x square over a square, that you have to differentiate with respect to x. So differentiation of x square is 2x with a minus sign. So minus 2x, right, divided by a square. So I wrote here, and you have exponential of minus x square over a square. So that simplification, you see that you have got this constant 2 here. So I can write down my and there is a minus sign here, there is a minus sign here, gives you positive sign. So 2ih cross ax divided by a square, exponential of minus x square over a square. Very simple. So you see, we find the product, operator product px with psi. So this second factor we have calculated, and now we will take our scalar product. So let us calculate this. So we start. So look at this. I take the scalar product of psi with pxi, which we want to find. So psi, pxi, and this is a bracket notation. So the integral notation is from integration of the argument will be psi star, right? Is a definition operating on pxi dx. Now you have psi star. So this you take a complex conjugate of psi star. So complex conjugate of psi star, there is no complex term here. So this is real, this is real. So psi star x will be psi x. Okay, psi star x will be the psi x. So anyway, look at the expression which I write down. So first I keep psi star as it is, and I put pxi. Pxi is this 2ih cross over a square ax exponential of this. So you can see I kept here 2ih cross, the constant a I kept it here, divided by a square, then exponential of minus x square over a square dx. I hope you understand this step clearly, right? This is very simple. We have a psi star. Uh, Psi star, I'm keeping psi star as it is, and I keep the value of pxi, and pxi I took this value. The only constant a I am just replacing here, and you have the exponential factor dx, right? And now let us see what happens when we calculate this. Now you put the value of psi star. So when you put the value of psi star, psi star means psi. So this is your psi. You see your psi is here. So that I will show you your psi. This is your psi. So once again it carries a exponential of minus x square over a square. So that psi I'm keeping here, right? And that is why you have a into a gives you a square, exponential of minus x square a square, and then this factor x, right? 2ih cross over a square, this factor exponential of minus x square over, look this factor. This a square appears because psi is consisting the constant a, psi star is also consisting constant a, so a is a square, exponential of minus x square over a square, and again you have this pxi is this, so this I am keeping 2ih cross divided by a square, exponential of minus a. This a is gives you a square here, right? So fine. So now look at this expression, and once you know this expression, keep all constant term outside. So I am keeping 2ih cross over a square is constant, a square is constant. I'm taking outside the integration sign. So now we have integration from minus infinite to plus infinite, and the integration is very known to you, x to the power of 1, right? And you have the exponential of this factor x, exponential of minus x square over a square dx. Now this integration you have studied is an odd of n. This you see, this is the odd function, x to the power of n, and you see how studied this integration second year BSc. Look at this integration from minus infinite to x to the power of n, where n is equal to 1 in our case, exponential of minus ax square, where a in our case is minus 2 over a square, right? Minus 2 over a square. So this is the value which we have got it for n, and here you see your n is odd, and if n is odd, then the integration comes out to be 0. So your integration is an odd function, and if the integration is an odd function, this integration comes out to be 0. So this is our integration. Here you see this integration which is carried from minus infinite. So your x is changing from minus infinite to changing to the plus infinite, and that is why you see your integrand. You see this integrand, and this integrand is changing here. And here you see I have mentioned the graph. You see your integration, look at that, this integration which I consider here, our integration, x to the power of 1 exponential of minus 2x square, this integration I consider, excuse me, करूँ फोन પછી करूँ. uh, so x to the power of, uh, you see in this case, x to the power of 1 exponential of minus 2x raised square dx. You see, if you plot a graph of y versus x, you can see, if you want to understand, this is our integration. I consider this integration is y, and if you plot a graph of y versus x, this is the nature you will get, right? This is the nature you will get. You see the for positive value of x, y is changing in this pattern, you see, and you see for a negative value of x, your y is changing in this manner. You can see that it is symmetrical. This graph, this is axis of symmetry of a function, and you see that ultimately the value from minus infinite to the plus infinite, this integration will give you the zero value, right? Because your n is odd is enough. N is odd, so integrand is an odd function. So this integration is zero. So there is a constant factor multiplied by zero. So yours the product which is asked in this problem is zero. So your answer of this particular question which is given to you, that the product side dx side, the answer is zero. So this is one example which gives you how to find scalar product for various eigenfunctions. Such problems are asked in various competitive examinations, so you please take care. Now here you see there is another problem which I want to solve. The Hamiltonian operator of a system is given, h is equal to minus d square by dx square plus x square. This is given to you. Show that a factor, this function n x exponential of minus x square by 2, this eigenfunction, you have to show that this function is an eigenfunction of your operator h. This is the operator h, and the problem is asked that this function of x, nx exponential of minus x square by 2, is an eigenfunction of Hamiltonian operator. Determine its eigenvalue and evaluate the constant, normalization constant, because this is a constant and this is psi of x. So psi of x is nx exponential of minus x square by 2, where n is a normalization constant. So we will find out normalization constant also. So this problem is very interesting, and it gives you many different view how to solve this particular problem. So now let us try to solve this problem. So you have your eigenfunction, eigenvalue equation. Your operator h is operating on psi, right? If psi is the eigenfunction of the Hamiltonian operator, then you have the E is the eigenvalue, and you have the eigenfunction is reproduced here. So now this is your eigenvalue equation, you know that, and this is our wave equations in quantum mechanics also. You are familiar with this equation. So now your h, so your h, I'm writing this, your h is minus d square by dx square plus x square, right? It is operating on psi, correct, is equal to E psi. So now we take the left hand side. This is the equation, right? So if this is the eigenfunction, this equation will be justified. So I take the left hand side. You look at the left hand side. Left hand side is minus d square by dx square plus x square, right? Uh, uh, and it is operating on psi. So what is psi? Psi is this nx exponential of minus x square by 2. So it is operating on psi. So this is your h, Hamiltonian operating on psi. So I put the psi. Look at this, convention I kept here. You have a nx exponential of minus x squared by 2. So now let us simplify this term. So if you simplify this term, you look at this, look at this. So you see the first term, you open the bracket, the curly bracket. The first term is minus d square by dx square operating on the entire function nx exponential of minus x square by 2, right? And the second term will be x square into nx. So it will be nx cube because n is a constant. So I can write nx cube exponential of minus x square by 2. So I hope this term is clear to you. So now again you go this way. Now you look at this. First of all, you see here I keep the second term, right? The second term here as it is. So I'm taking the second term as a first term because it's an addition. So I can write this nx cube exponential of minus x squared by 2. I'm keeping as it is. Fine. And you see there is a minus sign here. So I'm keeping this minus sign here. And it is a d square by dx square. So I operate, basically it is a d by dx operating on d by dx. So I take d by dx first. First I take the first differentiation because it is a second order differentiation. So first I take the first order differentiation. So first order differentiation is d by dx of this, right? D by dx of this. So this term. So d by dx of this term, this is a function of x, this is a function of x. So first I differentiate x and I keep this constant. Look at this. So it is basically n exponential of minus x squared by 2. Correct? Fine. Now you keep x constant and differentiate x squared minus 2. So you see I keep this my x. Fine. Look at this. N and a differentiation of x square minus exponential of minus x square by dx and you have the differentiation of minus x square. Differentiation of minus x square is minus 2x. So minus 2x divided by 2, right? That will be minus x square. So that minus x, that will be minus x. Minus 2x divided by 2 is minus x. Minus x into x gives you x square, and that is a minus sign. So this term is because of the differentiation of this term. So now you see this you get, now once again you differentiate. So when once again you differentiate, so you can see this differentiation. So now again you have the differentiation of n is constant and differentiation of exponential of minus x squared by 2. A differentiation of exponential of minus x squared by 2 is a function itself, and a d by dx of minus x squared, that is minus 2x. So there is a minus sign, and you see a minus 2x divided by 2, that will be minus x. So that's why you see there is a minus x only, and exponential of minus x squared by 2. So this term is known to you. This is simply a differentiation of n into exponential of minus x squared by 2, so that I can write it here. Now you see I'm keeping minus sign outside, and since it is a product of two function x square and exponential of minus x squared by 2, so first what I do, I first differentiate x square. So when I first differentiate x squared, it is 2x. So it is 2x, n is constant, and exponential of minus x squared by 2. And now you differentiate exponential of minus x squared by 2. So that is n x squared, right? And that is minus 2x divided with minus x exponential of minus x squared by 2. This is known to you. So now you see, again let us try to understand the simplification. So this is giving you nx cube exponential of minus x squared by 2. First term is as it is, and now you see I open this bracket. This is a minus sign, this is a minus sign, so it gives you x n, right? Exponential of minus x squared by 2 You see there is a minus sign here and there is a minus sign here. So it gives you plus. So it is giving you 2xn exponential of minus x square by 2. Now you see this is a plus here, and this minus sign gives you minus, and again this minus gives you, see that this will give you that is yeah, I'm sorry, there is a minus x square into minus x, that is a minus x cube. So this minus and this minus gives you plus, and there is a minus sign here also. So ultimately this when you open this bracket, you will have the minus sign here. The minus sign is basically this thing you have to verify. You have to write these steps after this class. You people have to write your own equations in your class note and verify the terms, right? This is the online class. So you please first understand the problem and then you write by yourself and derive each steps carefully and verify the steps. So you see these two terms cancels each other and ultimately you get phi equal to 3xn exponential of minus x square by 2. And this xn exponential minus is basically a wave function. So right, and so that is why what we, this is psi which is given to you. Look at this is the psi which is given to nx exponential of minus x square by 2. So uh, I can write my equation is simply, in our case, is h psi equal to 3 psi, you see. So your eigenfunction psi is the eigenfunction of h belonging to the eigenvalue 3. This is the equation is satisfied. So your eigenvalue is 3. So your psi is an eigenfunction, right? H psi equal to E psi. This equation is similar to H psi equal to where E is the eigenvalue is 3. So the eigenvalue of the operator, say right, see this, psi is the eigenfunction. So the eigenfunction of an operator H belonging to the eigenvalue is 3. So this is the energy measurement. You are getting the value 3, correct? And now we want to study the normalization constant. The normalization constant condition, you see I write the condition for normalization. Integration of psi star psi is equal to 1, right? From minus infinite to plus psi star. So your wave function nx exponential of minus xy, because it is the complex conjugate. Each term is real, so your wave function remains as it is, nx exponential of minus x square by 2. Again, nx exponential of x square minus by 2, right? So these n and n gives you n square, x into x gives you x square, and exponential of minus x square by 2 into exponential of minus x square by 2 gives you exponential of minus x square. And this integration, you see this integration is similar to the expression which is, this is a standard integration. What's the psi? I wrote this integration from 0 to infinite x square exponential of minus ax square dx. Please remember, the integration, the lower limit is 0, the upper limit is infinite x square. So here also you have x square exponential. So here also you have, you see here also you have basically exponential minus ax square. So here your a is equal to 1 in our case. This is dx, so this is dx. And you see this is minus infinite to the plus infinite. This is 0 to infinite. So our integration is from minus infinite. So I have to multiply by 2 if you want to write down from minus infinite to the plus infinite. So the value of 0 to infinite is root pi by 4. You see root pi by 4, right? Into 1 upon a raised to 3 by 4. So this is the integration. But I have to multiply by 2 because it is carried out from minus infinite to the plus infinite, and you have a multiplier constant n square. So n square 2 root pi by 4 1 upon and this is A is 1, and so that is why the value of you get 2 upon root pi and raised to half. This is you can verify. I have calculated this value. I hope this problem will help you to find under for normalization constant. Of course, you have work out problems in second year BSc to find normalization constant. So you see, these problems will give you a understanding to find normalization constant. And now there is a very interesting example which I want to present. You see, there are two operators here. You have another example which I would like to present, that you have an operator A and operator B. These are the operators which commutes with their commutators. This is the conditions given to you, that there are operator A, operator B, and they are commuting with their commutator. So you this way, operator A operating with a commutator of AB, and this is simply you can write they commutes with each other. So I can write commutator of AB operating on B. This I can write. Similarly, a operator B is also commuting within a commutator of AB. So this I can write down. This product, operator products, I can write down the commutator of AB operating on B. What we want to prove that the commutator of A with B to the power of n, commutator of A with B to the power of n should be equal to n B to the power of n minus 1 into commutator of AB. This we want to prove. So you see, I can take this analogy first. You see, first I take the commutator of A and B. So I can write this commutator of AB simply a product of 1 into commutator of AB. This is I can write. And this is simply a 1. I can write down 1 into B to the power of 0, a commutator of AB. Now you can compare this rule. So you see this A B to the power of n. In this case, n is equal to 1. So this is n equal to 1. So for n equal to 1, this law is satisfied, right? For n equal to 1, this law is already satisfied. So we can say the result is true for n equal to 1. It is already established here. Because you see, I can write AB, commutator of AB is equal to 1 into commutator of AB and 1. I can write in this manner. Okay. Now, let us go for n equal to 2. We want to generalize this result. So, when you go for n equal to 2, we have a commutator of AB square. Because you see our problem, you see what we want to prove. A B to the power of n. Here I am taking n equal to 2 now. Fine. So now when I am taking n equal to 2, so A B square. So now I can rearrange this commutator is equal to the commutator of A, and the B square is nothing but the operator product of B into B. Right. So now you can see this is a commutator law, common commutator, which I taught you yesterday. The commutator of ABC, commutator of A with BC is given as commutator of AB operating on C plus commutator of B operating on AC. This is C here. Please remember, this is not printed. So this is B with a commutator of A with C. So this is a letter C here. So now you can see, so this is, we can compare. So this is your operator A, this is operator B, this is operator C. So we can write down here, you see, operator AB. So operator AB is here AB, so it is AB. And then you write down this is operator C is B, so I write operator C here B. Then I write down B, so operator B is again in your B, so I'm writing B. And then it is AC, so A is operator A and C is operator B, so I'm writing operator B. Right now you see I'm writing, this is nothing but You see this, I can, this is, you please try to understand. Your operator, a commutator of AB operating B. Here I am writing now B first, and B is followed by a commutator of operator AB, because your operator B is commuting with the commutator of AB. This is the law, which this is the condition given, and since this condition is given, I can write this: the commutator of AB operating on B is equal to operator B operating on a commutator of A and B, because these B and the commutator of A and B are commuting with each other. So this condition I can write here. So I write down this condition here. And again you see this is C. So this is 2B, right? This is B and B. So 2B operating on NB. So this I can rearrange 2 times B to the power of B to the power of 1. So I can write 2 minus 1, an operator of AB. So now you see, and for the result for n equal to 2 also, you see this result is n equal to 2, n equal to 2, B to the power of 2 minus 1, AB. So you can see that we have derived for n equal to 2 also this result is correct. So let this result to be true for n equal to k. Let us consider that this result to be true for n equal to k. So if it is n equal to k, right? So we can write down, you see this equation a b to the power of k. So you see this relation here, a b to the power of k should be equal to k b to the power of k minus 1 ab. This you should write, right? So that's why I can write here k b to the power of k minus 1 ab. Okay, and now let us consider I take to derive this, right? Now for n equal to k. And now you see these conditions, I wrote this particular equal to. So now what I do, I take a operator A, right? And I take this operator A with us another operator which is with the operator B to the power of k plus 1. Here I am writing B to the power of k plus 1, because I want to go for n equal to k. So I just take this term A b to the power of k plus 1. So this is simply b to the power of k plus 1. I can write down A b to the power of k into the b. This I can write. Okay, and again you see this is I'm taking operating on ABC, right? So this is the operator AB operating on C. This is the law, this law which is given to you. I hope you know this law, right? So this law I'm applying again this commutator law. So this you can see here. So I can write this law here. So you please remember this is the factor, and we can write down this. Okay, so this A b to the power of k of operating on B plus, you see, B. So this is B is b to the power of k, and the commutator of A and C. Commutator of A and C is A and C is B. So this is I think you can understand now, right? And now let us see how you can write. Now you see this commutator is the commutator of A with B to the power of k. This commutator is already calculated for n equal to k, right? Commutator of A b to the power of k. This result we have already obtained, that is k. So k b to the power of k minus 1, b to the power of k minus 1, commutator of AB, commutator of AB. So this value is given here into B, so into B, and this is b to the power of k, and this is the commutator of KB, right? And now you see this is this result, you see that is k operating on B, k minus 1, and you see this one again This is the same rule. They commutes with each other. A commutator of AB commutes with B. So if a commutator of AB commutes with B, so I can write down k b to the power of k minus 1, and I write this commutator law, and this is b to the power of kab, right? So you see, I get this term. So I can write down k b to the power of k minus 1 into b, because this is b, ab, b to the power of k, and the commutator of this. So this result I'm writing here, k b to the power of k minus 1 into the b, that is b to the power of k, commutator of AB, and then it is a b to the power of k commutator of AB. So this term you can take it outside, b to the power of k and commutator of AB. So it is a k plus 1, right? So you see this is k plus 1, and you can write k plus 1 b to the power of k AB. Look at this. I hope you understand this step. So commutator of a b to the power of k plus 1 equal to k plus 1. You see, this is b to the power of k. B to the power of k, I can write b to the power of k plus 1 minus 1, because 1 cancels. AB. So now you compare this result with our previous result. You see, this is a b to the power of k plus 1 equal to k plus 1. Suppose instead of k plus 1 you put n. So a b to the power of n equal to n, right? B to the power of n minus 1 ab. If k plus 1 is replaced by n, then you will get a b to the power of n, that is a commutator of a b to the power of n equal to commutator of, it calls factor k plus 1 b to the power of, that is n, k plus 1 is replaced by n, so n b to the power of n minus 1 ab, and that is what we want to prove. See, n b to the power of n minus 1 commutator of ab. So this is ultimately a simple problem, and so that is why you can now you see that the result is true for n equal to k plus 1. Hence, for any positive number n, one can write a commutator of a with b to the power of n is always equal to n b to the power of n minus 1 commutator of ab. I hope these results are sometime useful for some other problems. So this particular problem giving you a practice to solve a commutator relations. So you please concentrate, and I request you that once my class is over, you please derive by yourself. I have shown the method, I have discussed each steps in detail. So you have to derive it separately and compare the steps and find out the results. And there are some other problems, homeworks I will give you in an assignment, so that will give you the problems, so that will give you a practice to solve certain tricky problems also. Now there is a very simple problem which we would like to solve. You see, this problem is that show that eigenfunction psi equal to sine k1 of x, sine k2 of y, sine k3 of z is the eigenfunction of the Laplacian operator. This we want. Such problems are asked in you see some competitive examinations. Now you people have to go for NGP examinations. Sometimes you have to go for GEM exams, and even after graduations you have to appear for NET examinations, RET examinations. So these examples will help you you see to have a practice for the competitive examinations. Look at this problem now. So we want to show that this eigenfunction is this function of x, psi of x, is an eigenfunction of a Laplacian operator. The Laplacian operator is del square. And so del square operating on psi. So I'm just taking del square operating on psi. So if I say that del square operating on psi, you should get some eigenvalue, and then it should, so you should get a relation del square psi equal to some constant c into psi. So your equation, if psi is an eigenfunction, then you will get your equation del square when del square operates on psi. That result, this operation should comes out to be equal to some constant into psi that you want to prove. So I take del square operating on, so del square is operating on psi is a sine k1 of x, sine k2 of y, sine k3 of z. So I write it here. Okay, now del square is a Laplacian, so it is del square by del x square plus del square by del y square plus del square by del z square operating on sine k1 of x, sine k2 of y, sine k3 of z. Now you can write down the separate equation, because this is the complete operator and it is operating on operand. So now if I solve this bracket, so I can write down del square by del x square operating on sine k1x, sine k2y, sine k3z plus del square by del y square operating on sine k1x, sine k2y, sine k3z, and plus del square by del z square operating on sine k1 of x, sine k2y, and sine k3 of z. Right, so this you have it. Now let us see, this is very simple. Del square by del x, so there are second order differentiation. You see, this is with respect to x, so sine k2 of y and sine k3 of z remain constant. So first you take the first differentiation, so del by del x of sine k1 of x, so it will be k1 into cos k1 of x, sine k2 of y, k3 of z. Again you take a differentiation del by del x again, because it's second order, so it is a cos k2 of I'm sorry, cos k1 of k1 into cos k1 of x, right? It is a k1 is a constant, cos k1 of x. Now differentiation of cos is minus sine, so it is minus sine k1 of x, k1 of sine k1 of x. So k1 is already present, so it will be minus k1 square sine k1 of x. This is simple. And the remaining term sine k2 of y and sine k3 of z is the remaining constant. So here del square by del x square of sine k1 of x, sine k2 of y, sine k3 of z is minus k1 square sine k1 of x, sine k2 of y, sine k3 of z. Similarly, you have now del square by del y square. So instead of taking k1 square, now it will be k2 square with minus sign, and sine k1 of x, sine k2 of y, sine k3. Similarly, instead of having a k2, now you have a k3, right? So this I can write down here. This is minus k3. So minus term is also here. Uh, I think I have not mentioned that my minus term, minus k3 term, but it is already there. So when you solve this, minus k1 square, minus k2 square, and then you have minus k3 square, minus k3 square sine k1 of x, sine k2 of y, sine k3 of z. That term is missing. So please note down, this term is missing here. So you please note down, and then you can take sine k1 of x, sine k2 of y, and sine k common from all the terms. So you have got a minus k1 square, minus k2 square, minus k3 square, right? And that is equal to, and this is basically, you see, sine k1 of x, sine k2 of y, sine k3 of z. That is simply your psi. Look at this. This is your wave function psi, which is given. Sine k1 of x, sine k2 of y. So your wave function is again appearing here, as you see. So what we have proved, del square operating on sine k1 of x, sine k2 of x. This is a psi. So del square operating on psi, del square operating on psi is equal to some constant into psi. This constant is the eigenvalue, and the eigenvalue of operator del square, I would say. So what is that eigenvalue of? That is minus k1 square, minus k2 square, minus k3 square. So this is a simple problem, but sometime they may ask you in MCQ type problems or some other way your examiner can ask you to find out energy eigenvalue equations, to find eigenvalue problems also. So this will help you And now there is one more problem which I would like to discuss. You see, this problem is that show that a function e to the power of ik dot r, that is a plane wave, uh, right, propagating in the direction of r. Generally, we write this is the expression for a plane wave, which is propagating in r direction. So you have a plane wave expression. Show that this function e to the power of ik dot r is a simultaneously eigenfunction of an operator. Which are the two operators we have given? I mean, it is given minus IH cross del and minus H cross square del square. So we want to show that this plane wave expression e to the power of ik dot r is an eigenfunction of minus IH cross delta, and e to the power of ik dot r is also eigenfunction of minus H cross square delta. So first I take the first one, first eigenfunction. Let me see that I want to prove that it is an operator, right? So this function is an eigenfunction of an operator. So first I take this operator, minus IH cross delta. So minus IH cross delta operates on the function, the eigenfunction. Eigenfunction is e to the power of ik dot r. And so this is basically a gradient operator. It is a Dale operator. Dale operator is a differential operator. It is differentiating the function with respect to space coordinate. Here our coordinate is r coordinate. So we should take del by del r. So del by del r of I to the power of ikr. Right. So we can write down minus IH cross and e to the power of ik dot r is remain, and you have the del by del r of ikr. So that is ik. Right. So this you can write down. Okay, so now you can see, now you see that this is I into I gives you I square is a minus 1, and that is why this minus minus cancel. So your h cross k e to the power of ik dot r. So again you can see that your wave function, you see minus h cross square, see that so your look at this del now you can see the other way. We have to find the other, yeah, the first parameter is first operator for minus IH cross delta. What is the eigenvalue for minus IH cross delta? The eigenvalue is h cross k. Please remember, because you see this eigenfunction is reproduced. So what is the eigenvalue of e to the power of ik? Eigenvalue of e to the power of ik dot r is basically h cross k. And now you see we have the another eigenfunction, I mean another operator, I'm sorry, another operator, that is minus h cross square del square. So it is minus h cross square del square operating on e to the power of ik dot r. So I can write down it is minus h cross the del square is del dot del. So del operating on del of e to the power of ikr. And you see this equation again. You see so del, you see del operating on e to the power of ikr, that is ik. So ik I am taking outside, and again it is a del operator operating on e to the power of ikr. This is simple. And now again it will give you ik. So ik into ik is ik square minus h cross square e to the power of ikr. So your value will be, you see, I square is minus 1. So it is h cross square k square e to the power of ik dot r. So can I say that what is his eigenvalue? The eigenvalue is h cross square k square. Right? The eigenvalue is h cross. So in the previous case, minus IH cross delta. For minus this operator, for this operator is eigenvalue is h cross k. And for this operator minus h cross square delta square, what is the eigenvalue? H cross square k square. So e to the power of ik dot r is a simultaneously eigenfunction of operator minus IH cross delta and minus h cross square del square. I hope you can understand this problem now. So I have discussed enough problems for, you see, the operators, commutators of the operators, as well as the Hermitian operator, and you see the adjoint of Hermitian operators, which we have discussed. Now, next lecture onwards, we will study various postulates of quantum mechanics. My friends, I will give you some assignments now. In the assignments, I will give you some tricky problems which you people have to solve. And if you are facing any problem regarding the assignments, I have created the forum section. Please post your questions there. I will definitely solve your doubts. And you can also send me the email also if you are facing problems. Right? The questions are welcome. And now we will have a Google Meet, and I will let you know the Google Meet, and I will take your questions, your doubts, your query to solve your to solve your queries as well as your problems associated with the my unit number 4. Here I will stop. Thank you very much.